reactor is a susceptor. Here, the wafer will be held at temperatures around 400 degrees Celsius. The pressurized gases flow from their storage pads through high-purity electropolished stainless steel pipes. TEOS, or tetraethyl orthosilicate, is an organic liquid that has excellent conformal properties, but is difficult to vaporize. To transport TEOS like a gas, it is converted to a mist. A precision liquid injection system then sprays it into the pipes. These liquid and mass flow controllers regulate the rate at which gases are introduced into the chamber. The low-pressure chamber draws the TEOS and helium carrier gas along with the oxygen through these holes, which are designed to give the best conformality. The TEOS reacts with the oxygen to create silicon dioxide. The silicon dioxide grows evenly over the surface. Etching the layer vertically creates oxide spacers along the gate sidewalls. These SEM photographs show a top view of the sidewalls surrounding the gates. When the wafers undergo ion implantation again, the result is heavily doped regions with a lightly doped region protected by the spacers. This reduces the electric fields by spreading the voltage drop near the drain over the entire spacer region. This is an improvement over the self-aligned gate process and eliminates high electric fields concentrated at the edge of a heavily doped region. After doped regions are created, they undergo annealing at high temperatures using a rapid thermal process. Here, tungsten lamps reach high temperatures within seconds. This minimizes dopant diffusion and allows annealing to occur quickly. Inside the heating chamber, we can see 14 tungsten lamps. Each lamp has a tightly coiled metal filament stretched from end to end. Above the wafer, another 14 lamps provide an even distribution of heat. Polysilicon gates can withstand this heat, while a metal, like aluminum, would melt. Polysilicon, however, has a much higher resistance. For specialized chips that need to be fast, a thin film of silicide is deposited on the gate to decrease resistance. This is usually done as a CVD process by combining silane with a gaseous source of tungsten or titanium. In a cluster tool, one of the reactors is specifically assigned to this process. After deposition, the wafer moves into a rapid thermal reactor for annealing. Now a layer of insulating material is deposited to electrically isolate the polysilicon gates and transistor regions from the metal layers. TEOS is used as the silicon source for this process. To lower the thermal energy needed, dopants in the liquid form of trimethyl boron and trimethyl phosphate are added. In this system, the dopants are boiled together to create a vapor. With TEOS, helium gas is bubbled through the liquid. As the bubbles surface, they carry the TEOS into the system as moisture. When these vapors combine with oxygen, a layer of boron phosphosilicate glass, known as BPSG, is deposited. The new surface topography reflects the unleveled structures beneath. This is a problem for today's high-resolution photolithography. While a mask pattern can be focused precisely on the top surfaces, it can't simultaneously focus on the lower regions. These uneven steps can also create metal layers that are too thin and brittle. To eliminate these problems, the wafer surface must be planarized. To both electrically insulate the polysilicon and planarize the surface, a spin-on glass technique may be used. Here, a mixture of tiny glass particles is suspended in a solvent to make a thick liquid. When applied to a spinning wafer, the liquid fills depressions in the surface and rounds sharp features, resulting in a nearly planar surface. The wafers undergo a series of low-temperature bakes to evaporate the solvent. When annealed, the glassy film left behind forms a dense, high-quality insulating layer. Some of today's multi-layered chip designs require the completely flat surface produced only by chemical mechanical polish. After the contact holes have been etched, the surface again becomes non-planar and difficult for metal lines to cross. Metal plugs, usually tungsten, create the level surface needed to deposit the first metal layer. But first, a conductive material such as titanium tungsten or titanium nitride is deposited to serve as a glue and barrier. Although CVD is used to deposit some metals, most are still deposited